Okay, great. Thank you, Krista, for a wonderful introduction for CHC. And greetings to all jury members and my fellow Hyperloop researchers. So, I'm Siddharth from Avishkar Hyperloop, and I have Lokesh with me here, who will be presenting the infrastructure category for Avishkar Hyperloop. To start with the presentation, let me give a brief introduction about our team. So, we are a team from IIT Madras, India, and we are a very passionate team of 75 members working towards one goal, that is to develop scalable Hyperloop technologies around the globe. Let's start with the infrastructure part of this. So in infrastructure, we majorly have four aspects. One is the tube. The tube provides the vacuum systems for an Hyperloop to run through it. Next is the track. Track so that it supports levitation and propulsion. The civil part. Civil part has pillars and foundations which supports the track and the tube. And next is the vacuum systems. The vacuum systems are needed so that we can maintain very low pressures inside the tube. So let's start with the track. This is our track design. We have custom made track which supports levitation and propulsion and braking. So the track has majorly two sections in it. One is the F tracks, which are cantilevered outside the track, and they support levitation through an electromagnetic suspension. And the second part is the aluminum T track, which is in the middle of it and supports contactless propulsion through linear induction motors. The track has gone under a lot of FES simulations, and we have designed the track for a dead load of 2000 kgs with a factor of safety of 2.5. The materials are steel, which are used to make the F track, which support levitation, and aluminum, which is used to support contactless propulsion through LIM. So after the design of the track, we have manufactured in-house 30-meter testing track in our facility. So we have done a lot of testings on this. We have checked for tolerances and we did a pod run on it. So this is a 30-meter track which is elevated 1 meter above the ground, and it consists of 5 sections of 6 meters each. So the track is a continuous beam and is supported at 6 meters. Moving on to the tube part. So we participated in the competition in SpaceX and we realized the need of optimization of tube. So this is the tube which was made in SpaceX with a length of 1.5 kilometer, a diameter of 1.8 meter, and a thickness of 18 mm. So optimizing the thickness of the tube plays a pivotal role in the whole Hyperloop infrastructure. So we got the motivation to optimize the whole tube thickness. So what is our goal for this year? We want to manufacture a 500-meter tube, which is half a kilometer tube of 2-meter dia, which is vacuum compatible and helps us make a levitating pod run inside this. The cost of it is around it is estimated that the cost is around 2 million euros per kilometer, which is around 15 crore Indian rupees. So what is the cost plate of the whole Hyperloop? So the infrastructure accounts for the major cost of the Hyperloop, and among that, the tube and the track are the most expensive ones. In the tube, we have the material and manufacturing. Considering all these factors, the tube material plays a 26% and the manufacturing plays 13% role in the whole Hyperloop cost, which is really great and we need to think upon it. What are the possibilities to optimize these things? So our goal is to move from 18 mm thick tube, which was made in SpaceX, to a 6 mm thick tube. So we have to reduce the material cost. That can be achieved by reducing thicknesses and by having looser tolerances, which can be achieved by reducing the manufacturing cost. But there are some aspects, the other aspects too. So while you reduce thicknesses, you need to work on tighter tolerances, because at lower thicknesses, the tolerances play a very big role in their structural integrity. And also having looser tolerances would force you to go with higher thicknesses. As tolerances play a higher role in structural integrity, you need to incorporate those with higher thicknesses. So what exactly is our work? We need to find an optimum between these. So our main aim is to have an effective method which evaluates the whole tube and the tolerances and gives us a optimum design. So I have Lokesh with me, who will be who will be walking you through the design approach for the Hyperloop tube.
Thank you, Siddhant. So, moving towards the design approach for the Hyperloop tube. So, as Siddhant already told you, we have seen how tube play a major role in the cost effectiveness of the Hyperloop ecosystem. Now, to reduce the cost, we have to optimally design the tube, and for that, we have to look for the failure criteria of the tube. So now, as you all know, the cost is directly proportional to the thickness of the tube. So we need to optimally design the thickness of the tube. Now, coming to the failure criteria. So how a Hyperloop tube can fail? So we have two criteria here. One is failure by yield, another is failure by elastic instability. So what is failure by yield? As you all know, failure by yield is just when the stress generated in the structure due to the external load exceeds the yield strength of the material. That is when failure by yield happens. And to happen, like we need highest tube thickness, and which is economically inefficient because as cost is directly proportional to the thickness of the tube. Second is failure by elastic instability. So this is nothing but just buckling of the tube. So and why we are going with this approach is if we are able to estimate the buckling pressure accurately, we can able to predict the factor of safety of the tube, and by that we can able to optimize the cost. So as we can see, failure due to buckling. So here we have two examples which shows how a small perturbation can affect the instability of the tube and leads to buckling of the tube, which leads to failure. So this buckling mode can be very catastrophically. So now we are going with this method. So what are the challenges we have faced in designing the methodology for failure by instability? So as such, there are no proven analytical calculations which are available for validation of our experiments. Another is high dependence of the come from the manufacturing aspect, from the transportation aspect, from the erection aspect. So, and buckling pressure depends a lot on these parameters. So we cannot directly go with the linear eigenvalue buckling analysis or simple nonlinear analysis. We have to develop some methodology to accurately determine the buckling pressure. Now, to test our methodology, we are developing two kinds of experimental validation. First is destructive testing, another is non-destructive testing. So why we are doing destructive testing is to evaluate the buckling pressure through. We are doing this by experimenting a tube which will buckle at some stated pressure. Right. Another is non-destructive testing. In this, we are testing the structural integrity of the tube. So it will not buckle, but we want to see the deformation at such stated pressure. Now, what are the modeling approaches for fail by instability? So we have developed two approaches here. First is eigenvalue approach. Another is geometric imperfection approach. So what we are doing in eigenvalue approach is first we are carrying out a linear eigenvalue analysis. Then we are taking the output of this result, scaling it, and extracting the deformed mesh size. Then this extracted deformed mesh size will become the input of the nonlinear buckling analysis. And why we have this global deformation is because what we are doing in linear eigenvalue analysis is creating the global deformation due to this eigenvalue analysis, right? Another is geometric imperfection approach. So this can be done by two methods. First is deformation model in geometry. Another is deformation by load. So why deformation model in geometry is highly efficient, since these deformations and ovalities are random in nature. So we cannot predict the accurate locations of these imperfections. Second is deformation by load. So in this case, we are providing the deformation by load. So we are not as such modeling the deformations. We are applying the load before the simulations, before the nonlinear simulation, and those will act as a deformation imperfections in the tube. So now, what are the parameters affecting the buckling pressure? So stiffness, spacing, diameter, and tube thickness are the three parameters which will directly impact the buckling pressure of the tube. Now, what is our methodology? Is first we are fixing a buckling pressure. We are stating a buckling pressure that at this pressure, the manufactured tube will buckle. Then there are three parameters: diameter, thickness, and effective length. So we are taking input as a diameter and thickness, And for doing the nonlinear simulations, we need some input parameters. So let's say our buckling pressure is 0.2 megapascal, which cannot be the case because atmospheric pressure is 0.1 megapascal. So let's say we are designing a tube for 0.2 megapascal. Now we need some diameter. Let's say diameter is 2000 millimeter, thickness is 5 millimeter. Now we need length of the stiffeners. So we cannot directly jump into the simulations because we don't know the effective length of the stiffeners. So for the initial parameters, we have developed a MATLAB code using ASME standards. From those ASME standards, and we have done some manipulation in the MATLAB code. We are extracting the input parameters. So now we have diameter, thickness, and effective length. Now we are giving this to the nonlinear buckling analysis. And if the buckling pressure is greater than atmospheric pressure, it will be safe. And if it is safe, then we need to determine the deformation obtained in this atmospheric pressure. And if it fails, then we get to know the buckling pressure of the tube. So we are conducting this nonlinear buckling analysis after getting the input parameters from the MATLAB code, right? So these are the simulation results for our non-destructive testing. So as you can see here, like there are several graphs. So these several graphs tells us about the several scaling factor which we have taken. So we have taken scaling factor of 1, 3, 4, 5, 11, 13, 15. So these are done before the experimental validation. And after the experimental validation, we go through this process, and we found that a scale factor of 4 gives us the exact deformation versus pressure graph which we obtained through experimental validation. Now these are the simulation results for scaling factor 4. So in the experimental we got radial deformation of 8 mm, and in the experiments in the simulations we got the deformation of around 7.7 mm. So as we are quite close, this approach can be properly optimized. So this is a video of non-destructive testing which we have done in our testing facility. So this is a 3.6 meter tube, 2 millimeter thin tube. So as you can see, we are decreasing the pressure. Right now we were in 90 kilopascal. So we reached as a pressure of 100 pascals. So this is the non-destructive testing, and the buckling pressure of this tube was 160 kilopascal. So atmospheric pressure is 100 kilopascal. So we got a factor of safety of 1.6. 1.6. So we can accurately determine the factor of safety and thus accurately determine the cost. This is the experimental validation of the non-destructive tube. So from the strain gauge test, we got a stress value of 40 megapascal. So as I have already mentioned, like stress failure by yield is not the criteria in this case. So the failure mode is buckling. These are the results for the radial displacement. So what we have done is, one is non-destructive testing, another is destructive testing. So these are the results for the non-destructive testing. Now moving towards the destructive testing. So these are the simulation results for 0.6 meter diameter tube, which is 1.2 millimeter thin. As you can see, we got a radial deformation of around 3 mm and 40 kilopascal external pressure, buckling pressure. So these are the experimentals. As you have seen the catastrophic nature of the buckling in the Hyperloop tube. So during the simulation, you can see the graph between the deformation and the external pressure. During the simulation, we got an approx of 42 kilopascal because we cannot particularly state a particular pressure because buckling has some area. So where the pressure versus deformation curves becomes flatter, that means the stiffness of the tube will become 0. Then that is when the buckling happens. So we cannot accurately determine the point of buckling. So we got during experiments, during simulations, we got an external pressure of 42 kilopascal, and in the experiment, as you can see from the GUI, we got an external pressure of 39.28 kilopascal. And on the right hand side, we have seen the lobes which are formed in the experiments and simulation. So we have seen the five lobes in the experiments, and similar in the case of the simulations. These are the 5 lobes. Now Siddhant will take us to the conclusions and future ongoing process of the tube we are doing.
So thank you, Lokesh, for walking us through the design approach and design methodologies for the tube. So what is the conclusion of all the experiments and simulations? So we have found that the ovality of the tube has a significant role in the capacity of the pressure vessel. This ovality can be due to a lot of factors, majorly due to manufacturing and the loads which are applied on it. Next is the analysis. The nonlinear analysis is the way to go around these things. We need to perform analysis, nonlinear analysis, with giving global deformations to capture the correct behavior of the tube under external pressure vessels. Also, the testing has given us a approach which helps us estimate the accurate factor of safety for any tube. So through our testing, we can design any tube, and according to the factor of safety which we need, we are able to manufacture it. Also, the designs which we have made are validated through both types of testing, that is the destructive testing and non-destructive testing, with a marginal error of 5%. So this is the biggest validation for all of our simulations and calculations. So what is our future? What would we be doing in future? So we have 2 more prototypes which would be coming, and these 2 prototypes are of the same diameter but varying length. Now these lengths would be such that we have different buckling pressure. Now as you can see, we have tested the tube for 41 kilopascal of buckling pressure, and we would be testing 2 more tubes for 63 and 105 kilopascal pressure. After this, we'll be also manufacturing a 2-meter diameter prototype, which will be a smaller version of the 500-meter project which we are planning. Also, not only looking about the material optimization in steel, we also have to look about other materials. So we have manufactured one concrete tube prototype, which is a mix of both steel and concrete. So it has an inner steel tube with hooks around it, which grips onto the concrete casing around it. Thus, it provides extra structural integrity to the inner steel tube, and the vacuum compatibility of the whole thing is ensured by the minimum steel tube thickness inside this thing. So the next few steps would be in infrastructure would be, we have a 3.6 meter tube which was tested non-destructively. We have a 30-meter tube whose testing has also been done. Also, we have 150-meter tube which would be soon coming up in the campus which we have, and the 500-meter tube would be the 2-meter dia tube which we were talking about earlier, would be is under design review and would be soon under manufacturing. So yes, thank you for your time. Thank you everyone.
Thanks, guys. That was great.
Yes, we are open for questions.
Yeah, if anybody has any questions, feel free to turn on your camera and start talking, or you can type it in the chat if you wish. I have a question to start off. So all this track building is very expensive. So how are you guys managing your sponsorship and getting funding for this?
Okay, so to answer this, yes. So to answer this question, I think there's a question. Okay, so basically, to answer this question, we have to for any team to approach sponsors, they generally approach through to telling them to, through the pod side. But there is a major stuff which goes around the pod, which is infrastructure. So we have different sponsors for infrastructure too, and we are backed by Indian Railways, who would be helping us to manufacture the 500-meter tube, which is upcoming. So we have different sponsors for infrastructure, and we have different sponsorship for the pod.
Cool. Wow. And so who are your main sponsors for the track?
So we have, actually, there are a lot of sponsors. So we have basically the whole project is sponsored by the Indian Railways, and they'll be sponsoring for everything, the vacuum systems, the foundations, the tube, and the track. Along with that, we have a lot of sponsors like Tube Investment India, Bharat Benz, which sponsor us on the pod side and the tube side as well.
Wow, that's amazing. Looks like we're gonna have a Hyperloop competition in India next year.
Yeah, sure.
Looks like we have a question from Alex. What material did you use? Also, did you look into thermal expansion and contraction over the length of the tube in traditional oil and gas settings? There we go. The product itself maintains
Expansion of the tube
in conjunction with the ground, keeping the external temperature stable.
Hello, am I audible?
Can you guys hear me? Yeah?
Hello, am I audible?
Okay, yeah. If you guys just open the chat, you can see the question that was asked. If it was, what material did you use?
Am I audible?
Yes, we can hear you. Mm-hmm.
Yeah, we do consider this thermal expansion of the tube as well as thermal expansion of the track as well. So for thermal expansion of the tube, we are searching for a novel methodology. So as such, like we have this thermal expansion bellows, which we primarily use in the small pipes and tubes. But since the diameter is 2 meters, so we are looking for some novel methodology. So that is what we are doing for the thermal expansion. So we are also testing this 2 meter long customized thermal expansion bellows, which is already in the market. But we are also looking at the research aspect of this thing. And answering the what material did you use is like right now we are using this mild steel. So as I've already said in the presentation, like we have two methods. So one is failure by yield, another is failure by instability. So failure by yield, we have to think about the material strength, but we are going with this. The primary mode of failure of this Hyperloop tube is buckling, and buckling for buckling it is happen much below the yield strength of the material. So we can go for the mild steel because Young's modulus for all the steel will be approximately same, right? Young's modulus don't depend on the carbon content and the type of steels generally. So we are looking for the cheapest material, which is mild steel, and looking on the availability aspect of the material also. So the major concern is the Young's modulus of the steel, not the yield strength of the material.